So this is a brief outline of what I'll cover. I'll first give a brief overview of the problem of wheel squeal before talking about some efficient modelling we've done on to predict friction modified squeal, and in particular introduction of an instantaneous rolling contact mechanics curve, and finish with the results both experimentally and from our models. This is an example of wheel squeal. I'm sorry, it's a very annoying tonal noise that occurs as a train goes around typically a sharp curve. It's exciting one mode of vibration typically, a lateral mode of vibration which is excited by lateral sliding, which is governed by this lateral creep curve. And the conventional mechanism is that the falling slope of this creep curve introduces power input and excites this mode in a similar way to a bow exciting a violin string, a natural frequency of a violin string. And you can also create your own squeal in the dining room. If you've got some wine glasses, you can simulate the train going around the curve of the rim of the glass, and under the right friction conditions, you might need to dip your finger in, you can make a wine glass sing using the same mechanism. Friction modifiers have been successfully used to reduce the sound pressure level of squeal noise, typically because they get rid of this negative slope, but they don't always eliminate wheel squeal. So here's an example here of our test rig where we tested under dry, water-based friction modification and oil-based, and even though the lateral creep curves had a positive slope or non-negative, we still got squeal. So the squeal's indicated by typically above 100 dB measured on the test rig. So some efficient modelling we've developed to predict wheel squeal is based on this concept diagram shown here, where we have the contact mechanics interacting with the vehicle curving mechanics. We've identified some critical parameters associated with that interaction, and it excites a modal dynamic of the wheel. So we pick out suitable, or we can look at multiple modes, getting excited by that lateral creep curve. I'll talk about a squeal limit cycle analysis, because the squeal is an exponential growth to a nonlinear limited amplitude, and that's the amplitude you hear. So it's a limit cycle analysis, and that vibration gets transmitted via acoustic mechanics to the ear. So the dynamic model is shown here, our analytical models based on a single mode of vibration. This lateral mode, typically we have 3 nodal diameters. It's very efficient at transmitting sound, and it's excited via this lateral creep curve, and in particular when you get over to this negative damping region. A little bit more on that, you can see when the squeal occurs, along with the vibrations of the wheel, you've got oscillations in creep. Now, it's this negative slope region which is actually causing the growth of the vibrations there. So to cut a long story short, in order to predict this limit cycle amplitude, we looked at the problem in terms of an energy balance. So what happens is the squeal vibration grows until the creep oscillates over to the positive side of the curve, where energy is actually dissipated along with the damping in the vibration mode. So I'll cut through the maths quickly, but because it's just based on that energy balance, but based on that we fortunately came up with an analytical solution for this vibration amplitude as a function of those critical curving and lateral creep and modal dynamics parameters. And this is extremely efficient for us to look at a wide range of parameters very efficiently. Okay, so in order to, I suppose, validate our modelling, we use this 2-disc test rig where we have quite a large wheel disc which represents the wheel, and a smaller, more solid disc, and this disc has a similar mode of vibration as the real wheel. In order to model the effect of friction modification, we looked at some of the theory and realised that there's a friction coefficient rises under friction modification due to an increase in temperature. But these temperature effects are expected to be slow compared to the oscillation of squeal, which is above 1,000 Hertz. So the time constant of the temperature dynamics will be much slower than the squeal itself. So what that means is when we do a measurement of the creep curve, we're just measuring the quasi-static creep. But what we can do is back infer what the instantaneous creep curve would be. So for each point on the quasi-static curve, you've got an oscillation that occurs instantaneously, but averages out to the same point on the creep curve. Hopefully that's a bit clearer here, where we have squeal growing as the green dot. You see it oscillating as we're squealing and averaging out to a quasi-static measurement of the lateral creep curve that you'd measure as the thin curve there. So based on this analysis, we were able to predict the steady state amplitude of squeal under both dry and friction modified conditions. That's showing the simulations. Our analytical prediction is shown there, which is reasonably close. And this curve here is showing the range of creep oscillations that occurs under the dry and friction modified conditions. And I suppose the key thing to note is that even though the friction modified curve, the measured curve has no negative slope, the instantaneous curve does, and that's the reason why we're still getting squeal in this case. Based on that, we could then work out the sound pressure level based on the acoustic mechanics. So in the dry condition, we have our analytical solution shown there over a range of angle of attacks is on the x-axis. Our simulation, which uses a more accurate creep curve, is reasonably close, and our test rig measurement results show a fairly good trend with angle of attack. You'll note we're overshooting at these low angle of attacks where typically squeal is not occurring, and it's likely that we're measuring other sources of noise there. So we got squeal under the dry conditions. This is for a specific speed we were looking at, and similarly under the friction modified conditions we were also getting squeal. And again, we get quite a good match between our experimental results and the simulation and the analytical. So, in conclusion, we've developed a mathematical model for wheel squeal vibration and its amplitude and noise amplitude under water-based friction modifiers in this case, taking into account an instantaneous traction creep behaviour that we can't measure, at least yet, using existing technology. I should mention the mathematical model is based on the conventional mechanism of squeal, and there's a lot of research on other mechanisms such as mode coupling at the moment. So we've managed to back calculate instantaneous rolling creep curves based on our measurements of the quasi-static curves and predict the squeal even when it looks like the creep curve is not negatively sloped. This provides some insight into why friction modifiers have been shown to be effective in reducing squeal noise, but perhaps not reliable in eliminating the phenomena at all speeds. So in future, we'd like to do some further investigation of the effect of rolling speed and critical creep parameters under friction modifiers. Thank you.